that is an illustration of the way the equipment looks as if you were peering down into it from above. There are 1,000 LEDs in our large scale 300 millimeter, which is about 12-inch diameter reactor. And the photonic efficiency is afforded by the very even distribution of photons through the cross-section of that reactor, much more so than with an array of long, thin tubes in the cross-section. So it is an open tube. The inner sleeve is a quartz tube. There are an array of reflectors where the LEDs are mounted to, and that is what creates the shape that you saw in the previous slide. This is the fulcrum of our intellectual property and the basis of our patents, and why it is that we are able to compete with mercury lamps now when the electrical efficiency of our treatment technology is not as high as it is for mercury lamps. There is a hotspot in the middle. This is where the beams overlap. And in fact, one of the additional bumps in efficiency that we get is we swirl the water as it comes through the reactor, and that actually moves that hotspot back and forth with respect to dose. We also have an advanced oxidation process. Many of you will be familiar with a traditional mercury lamp and hydrogen peroxide AOP system. So we did some research into this and found actually that for our process, the ability to manipulate the wavelength gave us a huge advantage over treatment with hydrogen peroxide. We use a species of chlorine. We manipulate the pH a tiny bit to push around what species we're seeing. And we use actually 292 nanometer UV LEDs to achieve that hydroxyl radical formation, and actually also a little bit of chlorine radical. So the molar absorptivity coefficient is 13 times higher than hydrogen peroxide compared to 254, and 680 times higher than the traditional medium pressure lamp system. So we have reduced power demand, reduced chemical demand. We don't need a lot of chlorine to achieve the desired outcome, and there is no need for residual chemical quenching.